Good morning, children. Welcome to Samagra Shiksha Abhiyan, YSR, Kadapa District, Andhra Pradesh. Online video classes. My name is P. Sridevi. I am working as Physical Science CRT in KCBV, Karasapadu, Kadapa District. In the previous classes, we discussed about the first chapter of 9th class Physical Science, Motion. In that chapter, we learned so many topics. Those are speed, velocity, average speed, average velocity, uniform motion, non-uniform motion, acceleration, etc. topics are we learned there. Now we discuss about the second lesson of 9th class Physical Science, laws of motion. Okay, in this chapter we also discussed so many topics. Okay, so the mind mapping of laws of motion. Here the mind mapping. I'll have you see the picture. So in this chapter we learn force, Newton's three laws, first law, second law and third law, and some more topics we discussed here. Once again we repeat the main topics in this chapter. Force. Force is that which changes or tends to change the state of rest or the state of uniform motion of your body in a straight line. So, force changes an object's state of rest or motion, uniform motion. So, now we discuss about the Newton's first law. In Newton's first law, we learn about force and inertia. Force and inertia. What is the Newton's first law? Every body continues in its state of rest or of uniform motion in a straight line unless it is compelled by an external force to change that state. This is the Newton's first law. From this Newton's first law, we also learn another topic, inertia. The natural tendency of objects to resist a change in their state of rest or of uniform motion. This is called inertia. This is called inertia. Okay, now discuss about the Newton's second law. Newton's second law defines momentum. So, what is Newton's second law? The rate of change of momentum of a body. The rate of change of momentum of a body is directly proportional to the external force acting on it. Okay, rate of change of momentum of a body is directly proportional to the external force acting on it. Okay, now we discuss about momentum. What is momentum? It is the product of mass and velocity. Momentum is the product of mass and velocity. I hope you know very well. We denote mass with small m and velocity with v. But here momentum is represented with the letter P. So momentum P is equals to m into v. The SI unit of momentum is equals to kg meter per second. Okay. The same way CGS unit. CGS unit is equals to gram centimeter per second. Okay. Here we learn another topic, impulse. Another topic, impulse. It is the change It is the change in linear momentum of the body when a large force acts on the body for a short interval of time. Large force working on your body in a short time. So here impulse is denoted with the letter J. J is equals to F into delta T. So SI unit is equal to Newton second. CGS unit is equals to Dyne second. Okay, this is about the Newton's second law. Now discuss about the Newton's third law. Newton's third law related to action and reaction. Action and reaction. So for every action, there is an equal and opposite reaction. For every action, there is an equal and opposite reaction. Okay. Next, here we learn another topic, law of conservation of linear momentum. So when two bodies collides with each other, the total momentum of the system, before collision is to the equal to the total momentum of the system after collision. So total momentum of the system before collision is equals to total momentum of the system after collision. Here we observe an equation, m1 u1 plus m2 u2 is equals to m1 v1 plus m2 v2. Okay, now we come to the present lesson. At first, the ancient people thought that what is the natural state of the object when we leave it freely? What is the natural state of the object when we leave it freely? At first, Aristotle, a great philosopher. Aristotle is a great philosopher. He said that the natural state of the object is rest. The natural state of the object is rest. But he cannot give the explanation. Why the natural state of the object is rest. Okay. After some time, another scientist, Galileo Galilei, came and he stated that an object in motion will remain in same motion. If the object is in motion, it remain in same motion as long as no external force is applied. So without external force, the object is in the same motion. Without external force, the object is moving in the same motion. Okay, but he do two experiments to prove this. But he take a smooth surfaces. So first we observe the experiment 1. All of you see the picture. Here are three pictures. In first, marble rolls down a slope. Picks up speed due to the force of gravity of the earth. In figure 1b, the object rolls up an inclined plane. Its speed decreases because of gravitational force is downward. Object moving is upward, so its speed decreases. Okay, in figure 1c, marble is moving on a level surface. It has no reason to speed up or slow down, so it will continue to move with a constant velocity. Okay, so it will continue to move with a constant velocity. Now we observe another experiment. All of you see this picture. Here is also three pictures. So Galileo observed that in figure 2a, the marble released from its initial height. The marble released from its initial height rolled down due to the force of gravity and then moves up the slope until it reached its initial height. Okay, so marble reached the initial height. All of you see figure 2b. What is the difference between 2a and 2b? The slope is decreased. The slope angle is decreased. Okay, so he reduced the angle of upward slope. Then the marble reached same height, but it traveled more distance to reach the same height. So in figure 2b, the marble traveled more distance than figure 2a. Okay. In figure 2c, it keep on moving forever along the level surface at constant velocity. So, this type of experiments was done by Galileo Galilei. So, these are very smooth surfaces, but in our earth there is not that type of smooth surfaces. And also we learn in 8th class about friction. On earth everywhere there is frictional force, so it is impossible on the earth. So it is impossible on the earth. So after some time, after some time, one another scientist came. He was a great scientist, Sir Isaac Newton. Sir Isaac Newton. Sir Isaac Newton proposed his three fundamental laws, which explain the connection between force and a change in motion. Between a force and a change in motion. These three laws are popularly known as Newton's laws of motion. So these laws are called Newton's laws of motion. From these activities, we observe that the larger the net force, the greater the acceleration. If the net force is greater, acceleration is also greater. If the mass of the body is constant, and also larger the mass, lesser the acceleration if constant net force is applied. So from these we can conclude that Newton's second law states that the rate of change of momentum of an object is proportional to the net force applied on the object in the direction of net force. So, F force of net force is equals to K into delta P by delta T. F net is equals to MA. F net is equal to MA. Here M is mass, M is acceleration. M is mass, M is acceleration. The SI unit of force is equals to kg meter per second square. kg meter per second square. This unit has been named in Newton. Kg meter per second square is equals to 1 Newton. Okay. Now we discuss about the Newton's third law. Newton's third law. Newton's third law of motion. If one object exerts a force on the other, one object exerts a force on the other object, the second object exerts the force which when acts on the first one with equal magnitude but in opposite direction. So Newton first law and second law work only a single object, but here in third law there is two objects. One is action object, another one is reaction object. So Newton's third law have two objects. Okay. In our daily life there are so many action and reaction activities. For example, motion of rocket and birds fly in air, and also fish swims in water, etc. Okay. Now we observe some activities. All of you see the picture. Pulling two spring balances. Pulling two spring balances. All of you see here there is two spring balances. Let us take two spring balances of equal calibrations. Connect the two springs balances as shown in figure. Pull the spring balance in opposite direction. Pull the spring balances in opposite directions as shown in figure. According to third law of motion, when an object exerts a force on an other object, the second object also exerts a force on the first one, which is equal in magnitude but opposite in direction. So here two opposing forces are known as action and reaction. So if the first spring balance force is action and the second spring balance force is reaction. Now we observe another example. All of you see there is two objects. Here is two objects. The force FBA exerted by the object A on the object B. The force FBA is exerted by the object A on the object B is equal in magnitude and opposite in direction to the force FAB exerted by object B on the object A. So force of AB is equals to minus force of BA. So both forces magnitudes are equal but directions are opposite. So from these two activities we conclude that Newton's third law is working on two objects. Okay. Now we discuss another example. All of you see when rocket is moving in the sky. All of you see rocket is moving in the sky. When the rocket is moving towards front, the gases. The gas is released backside of the rocket. Backside of the rocket. The rocket move towards front is action. The gases moves opposite direction is reaction. Okay. Here, a rocket accelerates by expelling gas at high velocity. Rocket accelerates by expelling gas at high velocity. The reaction force of the gas on the rocket accelerates the rocket in a direction opposite to the expelled gas. It is shown in figure. Okay. Now we discuss another topic, balloon rocket. How we prepare balloon rocket? Inflate a balloon and press its neck with fingers. Inflate a balloon and press its neck with fingers to prevent air escaping from it. To prevent air escaping from it. Pass a thread through a straw and tape the balloon. Pass a thread through a straw and tape the balloon on the straw as shown in figure. Hold one end of the thread. Hold one end of the thread and ask your friend to hold the other end of the thread. So one end of the thread you hold and the other end of the thread your friend hold. Okay. Now remove your fingers from the balloon's neck. Now remove your fingers from the balloon's neck. So as to release the air from the balloon. The air released from the balloon. What happens? Inflate a balloon and tie its neck. The air within the balloon exerts force on the walls of the balloon equally in all the directions as shown figure 18. When we release the air, the balloon exerts force on the walls of the balloon equally in all directions as shown in figure. This is balanced by the elastic forces of balloon. This is balanced by the elastic forces of balloon. When we release the neck of the balloon to allow air to escape from the balloon moves in a direction opposite to that of escaping air. The momentum of the balloon and air is zero. Begin with when the air escapes with the same velocity. The balloon moves in the opposite direction to balance the momentum of the escaping air. First law of motion. Every body continues in its state of rest or of uniform motion in a straight line unless it is compelled by an external force to change that state. So, every body continues in its state of rest or uniform motion in a straight line unless it is compelled by an external force to change that state. Newton's first law explains what happens to an object when no net force acts on it. Newton's first law tells us what happens to an object when no net force acts on it. Okay. And also here we learn one of the topic, the natural tendency. The natural tendency of objects to resist a change in their state of rest or uniform motion is called inertia. So, the mass of an object is a measure of inertia. Mass of an object is a measure of inertia. If the mass is more, inertia is more. If the mass is less, inertia is less. Okay. The SI unit of inertia is kilogram. The SI unit of inertia is kilogram. Okay. Now we observe some activities. Now we observe some activities. All of you see the picture. In this picture, there is a bottle and paper hoop and pen cap. So here we observe the motion of pen cap kept on thick paper ring. The motion of pen cap kept on thick paper ring. Okay, make a circular strip from a thick paper. Make a circular strip from a thick paper. Balance the ring on the center of the mouth of a bottle. Balance the ring on the center of the mouth of a bottle. Now balance the pen cap on the paper ring. Balance the pen cap on the paper ring. Aligning it on the center of the bottle's mouth. Center of the bottle mouth. Give the paper ring a sharp push. A sharp push with your finger as fast as you can. Sharp push with your finger as fast as you can. As you use force on the paper ring, you use the force on the paper ring. It comes into state of motion. It comes into state of motion. But the pen cap remains in its state or rest. So it fell into the bottle. So the pen cap is rest position. So it fell into the bottle. As long as no external force acts on a body, it remains in its state of rest. In its state of rest or motion. So this is called inertia. This is called inertia. Now we observe another activity. All of you play very well carom board. All of you play. So here make a stack of carom. Make a stack of carom coins on the carom board. Give a sharp hit at the bottom of the stack with the striker. You can find that the bottom coin will be removed. You can find that the bottom coin will be removed from the stack and the others in the stack will slide down as shown in figure. Only the bottom coin is removed from the stack. Remaining are in the same position. Why? We applied force only on the bottom coin. So the bottom coin removed from that place. Remaining coins are in rest position. So we cannot apply force on them. So the remaining coins are in the slide down as shown in figure. Okay. So here also we observe that the inertia. Okay. There are two types of inertia. Those are static inertia, dynamic inertia. Static inertia, dynamic inertia. The body at rest always tries to stay at the same state of rest. If a body is rest, it always tries to same state of rest. It does not accept any change in its position. It does not accept any change in its position until some force act on it. Until some force act on it. This property is known as static inertia. This property is known as static inertia. Okay, next, dynamic inertia. The body which is in motion always tries to move in same direction. The body which is in motion always tries to move in same direction until some force act on it. Until some force act on it. This property is known as dynamic inertia. This property is known as dynamic inertia. Okay. Now we discuss about the relation between inertia and mass. The relation between inertia and mass. All of you see the picture. Here is a two wooden blocks. Two wooden blocks. If we apply same force from these two wooden boxes, which is with the same force, which move easily. So when we observe that the small wooden block moves easily, the big wooden block does not move easily. Okay, so inertia is a property of matter that resists changes in a state of motion or rest. It depends on the mass of the object. For example, the car has more inertia than a bicycle because the car have more mass than the bicycle. Okay. Mass of an object is considered as the measure of inertia. Mass of an object is considered as measure of the inertia. We know that SI unit of mass is kg. We know that SI unit of mass is kg. Okay. Now we discuss second law of motion. Second law of motion. The rate of change of momentum of a body is directly proportional to the net force acting on it. Net force acting on it. And it takes place in the direction of net force. It takes place in the direction of net force. Okay. Here we observe linear momentum. Linear momentum. The linear momentum of a body is the product of its mass m and its velocity v. That is, linear momentum is denoted with the letter P. P is equal to m into v. SI unit of linear momentum is equal to kg meter per second, or kg meter is equals to 1 Newton. So another unit is Newton second. Newton second. All of you see the picture. Here is different forces are applied on same objects. Different forces are applied on same objects. Larger the net force, greater the acceleration. Larger the net force, greater the acceleration. So, gently push a block of ice on a smooth surface and observe speeds up or how it accelerates. Now increase the net force and observe the change of speed. Increase the net force and observe the change of its speed. You will observe that when force acting is increased on the ice, its speed increases. If force is increases, speed also increases. That means its acceleration is also increases. Its acceleration is also increases. So from this we conclude that larger the net force, greater the mass of the body is constant. So from this we conclude that larger the net force, greater the mass of the body is constant. If the mass of the body is constant, net force is less, acceleration is also less. Net force is greater, acceleration is also greater. Okay, now observe another activity. Same force applied on objects of different masses. Here force is constant, mass is different. Force is constant, mass is different. Apply a force on an ice block. Apply a force on an ice block. It undergoes some acceleration. It undergoes some acceleration. Now take another block of ice with greater mass but apply on it. Now take another block of ice with greater mass but apply the force on it. The block undergoes a decreased acceleration. The block undergoes a decreased acceleration or move with less speed. From this, we conclude that larger the mass, smaller the acceleration. Larger the mass, smaller the acceleration. In constant net force, when constant net force is applied. Okay. Now we discuss about the lab activity, which tells us the Newton's third law. So the aim of the activity is to show the action and reaction forces acting on two different objects. To show the action and reaction forces acting on two different objects. All of you see the pictures. Material required. Material required. The required material are test tube, cork, rubber cork to close the test tube, and Bunsen burner, laboratory stand and thread, and also some water. See here, test tube, cork cap, string, Bunsen burner, water, stand. Okay, these are the material required to do the activity. Okay, take a test tube of good quality. Take a test tube of good quality glass and put small amount of water. In a glass test tube, take some water. Place a cork cap as its mouth to close it. Place a cork cap to close its mouth. Now suspend the test tube horizontally with the help of two strings as shown in figure. Suspend hanging the test tube horizontally with the help of two strings as shown in figure. Now heat the test tube with a Bunsen burner. Heat the test tube with a Bunsen burner until water vaporizes and cork cap blows out. Cork cap blows out. Observe the movement of the test tube when the rubber cap blows out. Compare the directions of movement of test tube as well as rubber cork. Observe difference in the velocity of rubber cork cap and that of recoiling test tube. Those are in different directions. So the cork cap is moving one direction and the test tube is moving opposite direction. Okay. So from this activity we conclude that action and reaction is working on two objects, but the magnitude of the force is equal but the direction is opposite. Okay. Now we observe conservation of momentum and impasse. Conservation of momentum. Conservation of momentum. Let us two objects with masses m1, m2. Two objects with masses m1 and m2 are traveling with different velocities. m1 and m2 are traveling with different velocities. u1 and u2 respectively with different velocities u1 and u2 respectively in the same direction along a straight line. So m1 and m2 moving a straight line with different velocities u1 and u2. But here m1 is greater than m2. m1 is greater than m2 and also u1 is greater than u2. They collide with each other. When they collide with each other and the collision lasts for time t, which is very small. The colliding time is very small. During the collision, the first marble, which have m1 mass, exerts a force on the second marble F21 and the second marble exerts a force on the first marble. Let V1 and V2 be the velocities of marbles. V1 and V2 be the velocities of marbles respectively after collision. So before collision U1, U2 are the velocities. After collision V1, V2 are the velocities. What are the momentum of the marbles before and after collision? Let us know from the table. All of you see the table here. Momentum before collision, momentum after collision, change in momentum, rate of change of in momentum delta P by delta T is there. For marble 1, momentum before collision is m1u1. For marble 2, momentum before collision is m2u2. For marble, momentum after collision is m1v1. For marble 2, momentum after collision is m2v2. Okay, change in momentum. m1v1 minus m1u1 for marble 1. For marble 2, m2v2 minus 2u2. Rate of change in momentum, that means delta P by delta T is equals to, for marble 1, m1v1 minus m1u1 by T, and marble 2, m2v2 minus m2u2 by T. So according to Newton's third law of motion, the force exerted by first marble The force exerted by first marble on the second marble is equal to the force exerted by the second marble on the first one. Hence, F12 is equals to minus F21. F12 is equals to minus F21. Hence, we get delta P1 by T is equals to minus delta P2 by T. Then M1 V1 minus M1 U1 by T is equals to minus half M2 V2 minus M2 U2 by T. After solving these equations, we get M1 U1 plus M2 U2 is equal to M1 V1 plus M2 V2. So here M1 U1 plus M2 U2 is the total momentum of the two marbles before collision. M1 U1 plus M2 U2 is the total momentum of the two marbles before collision, and M1 V1 plus M2 V2 is the total momentum of the two marbles after collision. So from these equations we observe that the total momentum is unchanged before and after collisions. The total momentum is unchanged, not changed before and after collision. All of you see the picture. In the picture there is a egg that is fall off on a concrete floor, and another one fall of an egg on a cushion pillow. So in this picture, why the egg is broken on concrete floor and why the egg is not broken on the cushion pillow? What is the reason between them? So here we observe that the time difference to reach the earth, is less for the egg on the cushion pillow. So there is one physical quantity, impulse. Impulse tells the reason of this. So impulse tells us the reason. And also in our daily life there are so many examples for impulse. Why does a pole valet jumper land on thick mats of foam? Pole valet jumper land on thick mats of foam. Is it safe to jump on sand rather than a cement floor? Why? So the reason is impulse. So a softer and more cushioned landing surface provides a greater stopping distance. A softer and more cushioned landing surface provides a greater stopping distance because of the longer time taken to stop. That's why the fielder pulls back his hands. While catching a fast moving cricket ball. Fast moving cricket ball. In this situation, the fielder is trying to increase the time to decrease its velocity. Fielder is trying to increase the time to decrease the velocity. Thus, the rate of change of momentum will be less. The rate of change of momentum will be less, so that the force of impact of the ball on hands will be reduced. So, the rate of change of momentum will be less, so that the force of impact of the ball on hands will be reduced. As we expressed the second law as F net is equals to delta P by delta T. Delta P by delta T. In order to minimize net force, you have to maximize the stopping time. To minimize net force, to maximize the stopping time. Then we get F net into delta T is equals to delta P. F net into delta T is equals to delta P. From the above equation, we know that the product of net force and interaction time is called impulse. The product of net force and interaction time is called impulse of net force. Impulse is equivalent to the change in momentum that an object experiences during an interaction. Impulse is equivalent to the change in momentum that an object experiences during an interaction. Forces exerted over a limited time are called impulsive forces. Forces exerted over a limited time are called impulsive forces. Okay, often the magnitude of an impulsive force is so large. Impulsive force is so large that its effect is appreciable, even though its duration is short. Its duration is short. Okay. From these, we conclude that when we drop the egg on a cushioned pillow, it does not break because a smaller force acts on the egg for longer time. Delta P is equal to F net into delta T. Even if the delta P is same in both the cases, the magnitude of the net force acting on the egg determines whether the egg will be broke or not. So, the fielder catches a fast moving cricket ball by pushing back his arms while catching it. If he does not pull his hands back, what would happen? The ball definitely hurts him. The ball definitely hurts him. When he pulls back his hands, he experiences a smaller force for a longer time. Smaller force for a longer time. The ball stops only when your hands stop. The ball stops only when your hands stop. This shows that the change in the momentum not only depends on the magnitude of the force, but also on the time during which force is exerted on that object. So, impulse is denoted with the letter J. Impulse is the product of a force F. Impulse is the product of force F and the time T for which it acts. The impulse of force is equal to the change in momentum that an object experiences during an interaction. So J is equals to m into delta V. It is a vector quantity. It is a vector quantity. The SI unit of impulse is Newton second. SI unit of impulse is Newton second or kg meter per second square. Kg meter per second square. Okay. Now we discuss impulsive force. Forces exerted over a limited time are called impulsive forces. Forces exerted over a limited time are called impulsive forces. Now this is the about to impulse. Okay, now we give some homework. So I'll have you do this homework. The force exerted by the earth on the ball is 8 newtons. What is the force on the earth by the ball? The force exerted by the earth on the ball is 8 newtons. What is the force on the earth by the ball? Okay. Second one, define Newton's first law. Third one is defines Newton's second law. Fourth one is define Newton's third law. These are the homework of this chapter. Okay. Thank you for giving this opportunity.